So the daily problem is minimize deviation in array, at least for another 5 minutes. But I'm trying to be consistent, and I just got home, so. But the gist of it is we have this array. You can multiply odds by 2 or divide evens by 2 every operation. So what's the minimum difference we can get between all the numbers, or the minimum maximum difference we can get? So here we could multiply 1 by 2 to get 2. We could divide 4 by 2 to get 2, and then we would have 2, 2, 3, 2. So the output's 1. Similarly here, we could multiply 1 by 2 and divide 20 by 2, and then divide 10 by 2, and then we would get 4, 2, 5, 5, 3, and then the output would be 3, because it would be the difference between 2 and 5. So it's an interesting question. I sort of rushed to do it. Anytime you have something like this where you're trying to maximize or minimize or maintain some sort of sorted pattern, and also you're repetitively performing these operations, a heap is a really good call, because you can pop something from the heap, you can do something to that element, such as dividing it by 2, and then add it back to the heap. And the reason why I choose divide by 2 as an example instead of multiply by 2 is because you can only do this once. An odd number you can multiply by 2, an even number you can divide by 2. But an odd number, the moment you multiply it by 2, it's not odd anymore. You know it's even, because now it's divisible by 2. So you can only increase each number once or 0 times. You can only increase it once if it's odd, or not at all if it's even. If it's even, you can decrease it, in theory, around 25 times, whatever power of 2 it could be. And I think that's also like sort of a sign of where to go with this problem, which is that like you want to find the maximum. You want to find the smallest maximum and the highest minimum and take the difference. So here, the smallest maximum you can possibly get is 3, and the highest minimum you can possibly get is 2. But the problem is, like, let's say this was 1, 2, 3, 1, 2, 4, 6, or something like that, where the lowest maximum isn't initially in the array. How do you know to divide the right things? And for the highest minimum, for that matter, you can imagine a scenario like here where we multiply 1 by 2. Okay, but why don't we multiply 3 by 2? And you could imagine a longer array where it's like, okay, fine, we have some shorthand for why we don't want to multiply 3 by 2, but here, why don't we multiply 3 by 2? Things like that. And it's not so apparent that, oh, well, obviously you multiply this by 2, you multiply this by 2, but you don't multiply this one. That's too large. Like designating something as too large to multiply by 2, or too small to divide by 2, because it'll mess up your answer, is an issue that sort of makes this problem more difficult than it initially seems. But it's not that difficult, because it turns out, like, if we use a heap, we can pretty much just brute force this and say, like, what's every single combination we could try, pretty much. Because at the end of the day, again, you can only multiply so many things by 2. And then dividing by 2, I mean, like, if every single number was a power of 2, worst possible case scenario, that's still only 20 or 25 divisions you're doing for each number. It's like log of the size of the number. So you can kind of just brute force this one, but the trick is you have to use a heap rather than every single time looking through and being like, what's the largest number? Can I divide it by 2? But that is basically what we're doing. We're taking a heap. We're taking a max heap. So this would go 4, 3, 2, 1, or whatever. And then we would take out the 4. We would say divide it by 2. That's now a 2. And then the next largest number is 3, and we can't do anything with that. So we've reached the minimum possible maximum. And the only other thing we need to do is take every single odd number and multiply it by 2, so that way this 1 would really be a 2. And then if we ran into it, let's say we find some situation where, hey, we want everything to be 1s, and we multiplied all the 1s by 2, we would just divide them all by 2, and then at some state in the heap, we would have everything being 1, and the difference would be 0. That's a little bit wordy and confusing, so it might help to write this out. So we're going to have something that's like a heap that represents all of the maximum numbers, potentially. But really, it's going to represent all of the numbers. But the reason why I'm calling it maximum and thinking of it that way is because this is going to be a heap. It's going to be a max heap, and the 0th element is always going to be the largest element. And what we're going to do is every iteration, we're going to take the largest element, divide it by 2, see if it's small enough that that's our new minimum element, and just keep track of our minimum element. And we're going to brute force every single possible combination of dividing or multiplying these by 2 that we can, up until we reach a situation where our largest element is odd, because in that situation we can't divide that by 2 anymore, so we can't really go any lower. There's not really any optimization to be made past that point, because the only optimization would have been to divide that number by 2. So anyway, you have that, and then we'll say minimum equals, we'll just say infinite, and then we'll say for num in nums. Actually, what we could do is say something like minimum equals, we'll say this, we'll say nums equals negative x if, okay, we'll say negative x times 2, bit shifted 1 is a confusing way of saying times 2, if x and 1, which is a confusing way of saying if it's odd. So we're saying multiply it by 2 if it's odd, or else just keep it, but we're making it negative. That way it fits into a max heap, because in Python, a max heap, you just kind of put the number in negative, and then it's a min heap of negative numbers, which is a max heap for x in nums. Okay, in fact, we'll just call this maximum. So now we have this nice little thing where we've multiplied every odd number by 2 and we've made everything negative. And once we do that, then we can heapify this. We're heapifying it instead of heap pushing everything, because this is O of n. If we heap pushed every single element, that would be nlogn. It's a weird quirk of heaps. So we've heapified maximum, and then we're going to say something like minimum equals, ironically, we're going to say maximum. This is still at the end of the day. I mean, we're treating it as a heap, but it's ultimately stored as a list. So we can just do list operations like taking maximum and minimum. So we're looking at the maximum, which because it's negative is going to be the minimum. And then from there, we're going to say something like while maximum at 0. We know that this will always have elements. There's no possible way that this isn't going to have elements. We say while maximum at 0 is even. So we'll say while not that and 1. And then we'll say something like current equals maximum dot heap pop maximum. That's the way to phrase it. The reason why you're performing a function on maximum rather than maximum dot heap pop is because, again, maximum is ultimately just a list. And this idea that it's a heap, this isn't some native data structure like a list node or a dictionary or something. This is like just the way we're treating this as a specific data type. That's just a list with specific rules. So, okay, we pop the maximum thing, and then we'll say something like, we want to take the difference between the maximum and the minimum and see if that beats out our current answer. So whatever state of multiplying and dividing whatever by 2, we want to see if that state has the smallest difference. So we'll say something like ans equals min ans, and we want it to be, it's going to be very confusing, but minimum minus maximum, because maximum is negative and minimum is negative. So really this is saying maximum minus minimum if they were positive numbers. And then we want to say heap push heap cur divided by 2. And we also want to update the minimum in case this is smaller than our current minimum. For example, if we had 3334 we would pop the 4, divide it by 2, and say, hey, that's smaller than 333. So now 3 was our minimum, but now 2 is our minimum. And again, there it wouldn't matter, because if this was 3334, the difference would be 1 no matter if this was a 4 or a 2. But still, like, if we're just brute forcing it, we want to say, okay, when it's 4, the first state is this is a 4, the minimum is 3, so the difference is 1. The second state of the 2 possible states are this is a 2, and now the maximum is 3, and the minimum is 2. So we recalculate 1. And we find out that they're the same because we keep track of the maximum. That's just maximum at 0. And we keep track of the minimum right here. So we say something like minimum equals, again, we have to say max, minimum, and cur divided by 2. And then return ands. I guess I want to dedicate a slight amount of effort to make sure that this is in the correct order and that the loop invariant is satisfied. So we're saying we start and there's a current state, and we're saying, okay, take out the maximum element, compare that to the minimum element, look at the difference and see if that's smaller than answer. See if the minimum element changes if we divide the maximum by 2 and put it back in, and then divide the maximum by 2 and put it back in. That logic's pretty sound to me. Oops. We don't want this to be minimum minus cur, because cur is our current maximum. Okay, that's another dumb error. Uh-oh. All right, I just ran into this issue. Oh, I know exactly what this is. This is just at the end we have to do this one more time, because we're comparing the answer and then we're taking the next state. So at the very end we need to compare the answer one last time. And there it is. It's interesting with these problems that are quite difficult to come up with a solution. And then the solution itself is just, I mean, you're literally just popping and pushing back into a heap. It's not all that complicated. I think maybe the thing that makes this difficult is that, like, I looked at this morning, and I just got back home and kind of hacked my way through it. But it's that you look at this, at least for me, I look at this and I go, okay, I could use a heap. I could do that. You could just brute force through. And it's an optimization to use a heap instead of iterating through and finding the maximum and minimum elements for every state that nums could be. That's true. But is O of nlogn good enough, or can we do better? And at least for me, I got pretty caught up with can we do better. I guess it's not even nlogn, it's nlog k, where k is the largest power of 2. Or like, yeah. But again, that can only go up to like 20 or 25. So it's an interesting problem. To be honest, I think I didn't explain it super great, but I'm just trying to pump out these videos right now. Hopefully the next one's a little bit more conceptually clear and interesting. Hit like if this did help though.